Hello and welcome to a lesson on applications of exponential functions. So we talked about exponential growth when the base of our exponential function was bigger than 1, exponential decay when our base of our exponential function was between 0 and 1. What makes an exponential function exponential is the fact that our variable is an exponent. And today we're going to basically put a little context into these exponential functions, okay? So if we're looking at a contextual situation and something is increasing exponentially in value or decreasing exponentially in value, we should be able to write an exponential function to model that increase or decrease. And there's going to be a couple of different scenarios. Now remember, what the basic form of our, like the parent function form of our exponential function was. We said y was going to equal some base to a power. So y equals b to the x power is sort of like our basic exponential model. But there's one extra component we're going to want to look at here. Now, I know that we can shift to the left and right and shift up and down, but we're not going to be so concerned with shifting our graph. What we will be concerned with, however, is the starting point of our graph, and that's going to be determined by what we put out in front. Let me get rid of this real quick. So a times b to the x power is going to be the form that we're looking at. So we talked about a. We know that if we put a negative out there, for example, it will reflect our graph, or put something bigger than 1, it stretches it, or put some fraction between 0 and 1, it compresses it. But it actually is a little more visible, the effect. Let me deviate here for a second. So when we looked at y equals 2 to the x, for example, or 3 to the x, or 4 to the x, or anytime that base was bigger than 1 and we had exponential growth, all of the functions looked like this. Now they might be steeper depending on what that base was, right? Maybe it did this instead, but the basic shape was the same, and they all crossed the y-axis at exactly 1 because anything raised to the 0 power is 1, right? So if I put a 0 in here for x, 2 to the 0 power would be 1. Well, if I put a number out in front of that 2 to the x power, so let's say I put a 3 here, well, if I put 0 in now, then anything to the power of 0 is still going to be 1. So 2 to the power of 0 is 1, but now if I multiply by 3, my graph would start up here at 3 instead. The rest of the shape would be maintained. Or let's say I put a 4 out there, then 2 to the 0 would still be 1, multiplied by 4 would then make my graph start at 4. Or whatever number I put out here is going to change the product, right? So 2 to the 0 power will always be 1, but if I now multiply by some number out here, that's where my graph will cross the y-axis instead. That's helpful to know if we're looking at a scenario. So in a contextual situation, right, we'll think about our x values being like usually time in a situation. The smallest time applicable is 0. So that's going to be the starting point for our situations, our context. And so the smallest x value being 0 means the starting point of our graph will always be seen by this number right out in front. Okay? So what we're looking at in our exponential functions, in our situations, is some starting point. Okay, so we need to be able to identify a. A is, again, the starting point. So it is like at time 0, or when x equals 0, where is the y value? Okay, where is the function value? That's our starting point. That's a. That is going to be part of our function every time. Okay, now b is a little more complicated depending on what you're given. So it could be that you're given 2 points on your graph. It could be that you're given a percent by which you're increasing, and it could be that you're given a percent by which you're decreasing. So to find b, if you're given 2 points, it should make sense. Okay, so again, think about y equals 2 to the x that we looked at in our previous topic. Okay, if we put in a power of 0, we get 1. Put in a power of 1, we get 2. Put in a power of 2, we get 4. Put in a power of 3, we get 8. And what's happening? What's happening with our y values here? Because our base is 2, we are multiplying by 2, multiplying by 2, multiplying by 2 to get from one y value to the next. So if we are given a table of values, right, let's say that in our y values here, we went from 1 to 4 to 16 to 64. Could we figure out what our base had to be for our function? Well, what am I multiplying by to go from 1 to 4, or from 4 to 16, or from 16 to 64 is 4, which means 4 had to be the base of that exponential. Now, sometimes our numbers aren't going to be as clear. So if we're trying to find what we're multiplying by to get from one number to the next, to work backwards, you could divide. So you could say, what's 16 divided by 4? And that means our multiple had to be 4. As long as they're consecutive values, you should be able to take a y value, divide it by the previous y value, and figure out what that base of that exponential had to be. That's like our multiplier. Okay, what are we multiplying by to go from one number to the next? Well, if we had to work backwards, we could divide. So to find that b, that base of our exponent, if you're given 2 points, what you're going to be concerned with are the y values. Take the second y value and divide it by the first one, or really any 2 consecutive y values. Okay, take 2 consecutive y values and divide them. Just make it sure it's the latter one divided by the previous one. So divide. You can always divide y values to find that base of that exponential. Now, if it's a percent, we have to think about what we're doing here. So in your initial value, so in your starting point, like in your car, for example, here, right? You have some car for this, the graph shows the value of a car over time. You have some starting value, and by what percent are you increasing or decreasing? We can actually see that in B. The starting percentage, the starting value, no matter what, is 100%. You start at time 0 with whatever you have with 100% of the value of whatever it is you're starting with, okay? Now you're either going to be adding to that value or you're going to be subtracting from that value. And the amount that you add or subtract might be given to you. So if you want to find B, and you're given the percent increase, you will literally just add that percent to 100 and then convert it to a decimal. So add the percent increase to 100, because you start with 100%, you add some certain percentage, and that's going to be B. Okay. Now if you're looking at a percent decrease, then again you're going to start at 100%, but then subtract the percent by which you're decreasing and convert to a decimal, and that's going to be your function. Okay, so we're going to try to write some exponential functions from situations. So let's look at example 1. Again, we have a graph that shows the value of a car over time. So at time 0, it says that the car is worth $20,000, which means buy this car $20,000. Now, this very next point says 1 year later, the car is only worth $18,500. So it's depreciating, and we can tell by the graph that depreciation is exponential, and we can see that it's going to flatten out here, right? There's going to be an asymptote in that graph. So we are asked to write a function, an exponential function, to model this scenario. So if I want to write an exponential function, I need to know 2 things. I need to know A, and I need to know B. A is the starting point of my graph. So the starting point or starting value in this car, the graph for this car, is $20,000. That's A. So we start out at $20,000, and then B is what am I multiplying by to go from my initial value to the very next value, the next consecutive value at 1 year. So it's kind of hard to see what am I multiplying by to go from 20,000 to 18,500, which is where we would work in reverse. So instead of what am I multiplying by, what am I multiplying by to go from 20,000 to 18,500? I'm going to work in reverse using division. So I'm going to take my second y value, 18,500, and divide by my first y value, which is 20,000, and that's going to tell me what b is. So what is 18,500 divided by 20,000? And it is 0.925. So my base of my exponent being 0.925 means I've gone from my 100% value down to now I only have 92.5% of its value. Okay, I've lost 7.5%. And again, my base being some fraction or decimal between 0 and 1 confirms that this is exponential decay. It is decreasing. Okay, so I know A and B, which means my model is going to be 20,000 times 0.925 raised to the x power. And so now we can confirm this. Let's go ahead and graph it and make sure the picture looks like what we have on our paper. Starting at 20,000, and then multiplying by 0.925 raised to the x power. Well, what am I doing? There it goes. Close that. Raised to the x power, and nothing is showing up here. That's because this graph is way, way, way up here at 20,000. So if I was to stretch this out, because my graph is pretty stretched. Alright, so it looks something like that, and we can see this graph is starting at 20,000. And if I moved my cursor along this graph, see if I can actually do that. So I can see that when I get to a year later, if I want to know exactly what's happening when x is equal to 1, let's just confirm. At x equals 1, there it is, my value down to 18,500. Okay, so we can confirm our function. Makes sense to do that. Now we can use the function. Part B says to calculate the value in 5 years. So the values, those are y's, and the years, these are x's. So when it says calculate the value, that means figure out y in 5 years. That means x is 5. So what can we do if we want to find y when x is 5? Plug it in. And that means in this case, y is going to have to equal 20,000 times 0.925 raised to the 5th power. And I put an x there. What the heck? Raised to the 5th power. And we can just throw that into the calculator. Look, I already have it here. So let me delete and put 5 up there. And so we end up with, since this is going to be a value, we'll round to the hundredth place, $13,543.74. That wasn't so bad. Okay, if we look at the next one, it says when is the car going to be worth 10,000? So when means we're looking for a year. That means x is unknown. Is the car going to be worth 10,000? Is telling us our value, our y, is 10,000. So a couple ways we can do this is we can do the same thing. We can plug the 10,000 in for y. Oh my, thought I had the eraser. We can plug the 10,000 in for y and solve this for x. Now, solving for x here, if we want to do this by hand, is going to be a little bit trickier because we'd have to use a logarithm to do this. Now, I'm going to show you how to do it. Now, don't write this if you are trying to take notes, or if you want to, it's up to you, but I'm going to end up erasing it because this isn't the way I would do it. Although it is an option. If you didn't have technology, if you didn't have a graphing calculator or something nice like Desmos, you'd want to solve this using logs. So you're going to divide both sides by 20,000, and that's going to leave you with all those zeros going away. It's going to leave you with a half, so 0.5 is equal to 0.925 to the x power. Now you can take the log of both sides, or you can just rewrite this. This would be the log base 0.925 of 0.5 equal to x. That actually wasn't too hard to solve, right? We're going to just put this into the calculator and get the decimal approximation. But since we're going to have to get a decimal approximation anyway, I probably would just use the function that's already in Desmos. So, let me go back here. Okay, so what we can do is the same thing we kind of do with regression, right? Remember when we get a model in here, if I want to calculate an x given a y or vice versa, I'm just going to put in, like I did here with x equals -1, the value that we have. So let me fix this function again. This was to the x power. If I want to know what's going to happen when y is equal to 10,000, I'm going to put that in there. Y equals 10,000 and see where it crosses my function. And then that point is going to tell me that when y is equal to 10,000, that x has got to be equal to 8.891. And just so you can see it, in the last one we put in x equals 5 to our function. We can also just put that in Desmos, and we can see that when x is 5, our y value is 13,543.74 cents, which is exactly what we did. So since we already have a function and we're already going to Desmos, then we can go ahead and just plug that x value into Desmos and find the intersection with our graph to get the y value that corresponds, or vice versa. Okay, so let me what should I show you here? Both ways. Let me go ahead and put the 10,000 in. And that way, I guess you have good notes to reference. If you were going to solve for x, you would divide both sides by 20,000. And that would leave you with a half, or 0.5, equal to 0.925 to the x power. And then rewriting that, we would have the log base 0.925 of 0.5 equal to x. And so x would be approximately, and just so you can see it, it's going to work both ways. If I put in the log base 0.925 of 0.5, I get that same value that I had here on my graph, which was 8.891. Okay, so 8.891. So when 8.891, so it's about 9 years. Okay, so in about 9 years. All right, so now you've got some options. The solving piece is what we did there in B and C. That's actually kind of old hat. The new piece was writing the exponential function. So let's try to do that again, and then we'll do some more practice with the old hat stuff. So it says in problem number 2 that Mila paid $300 for a certain stock in January of 2008. And it says the value of the stock was expected to increase by 7.5% per year. So we want to write an exponential function to model this scenario. So A is our starting value, starting point, and this one has a starting value of 300, and so A has to be 300 for this particular model. Now this one, to find B, I don't know the value of the stock in the very next consecutive year, so I can't divide values to figure it out. But this one's even easier. It's telling me to increase by 7.5%. So remember, we always start out at 100% of our value. If we're going to increase by a percentage, we're going to add that percentage to 100. If we're going to decrease by a percentage, we're going to subtract that percentage from 100. So all I need to do is add the 7.5% increase. So 100 plus 107.5 would be 107.5% as our multiplier. And so that's what B is. B is supposed to be 107.5%. Of course, we're going to convert that to a decimal to plug it in. So it would be 1.075 as a decimal, which means our function here is going to be 300 times 1.075 to the x power. And again, that base of our exponent being bigger than 1 is confirming that that's going to be an increasing graph. That's going to be growth, which is what we want here. And now we can do the same two things we did for B and C in the last one. This one says to calculate the value in 2020. And in our model, I used x and y kind of generically as variables, but x again represents time and y again represents our value. So this is calculate the value in 2020. In 2020 from 2008 there, that's 12 years. So that's x equals 12, and then find y. So I'm going to put this model into Desmos and not solve by hand this time. So we have y equal to, we started at 300, and then we have 1.075, that's 7.5% growth, and then raised to the x power. So there's our function, and there it is on our actual graph. Now we want to figure out when x equals 12, what's the y value that corresponds. So I'm going to put x equals 12 in there. It's going to cross my graph, and it'll say that when x is 12, that y is going to be 714.53. So the value is going to be approximately $714.53. And that was, again, obtained from the graph. Okay, and then we can do that again for part C. So in what year was the stock worth $900? So now they're telling us y is equal to 900 and asking us to find x. So I've got my function in here. This time I'm going to put in y equals 900 and look for that intersection. And that intersection says that when y is 900, that x is going to be about 15.191. So in what year? 15.191 years. Well, if we started in 2008, 2008 plus 15 would be 2023. So 2008 plus 15 takes us to in 2023, that's going to happen. All right, not so bad. Hopefully, not so bad. Okay, so those are some basic applications of exponential functions. The next few that we're going to look at revolve more around financial aspects and formulas. So I don't know if you're a fan of formulas, but these are formulas that incorporate exponentials. So the first one we're going to look at is called compound interest. So compound interest is, so interest, you should be thinking about that as a fee. If it's compound interest that you're either earning on some investment or being charged on some kind of a loan, the idea is with compound interest that instead of calculating that interest fee once for your loan or your investment, you're going to be calculating it multiple times over the course of your investment. And every time the interest is calculated, it's lumped into the amount that you invested or borrowed, and then when the new interest gets calculated, it's calculated on that amount you borrowed or invested plus the interest that was added in. So the idea is interest being charged or being earned on interest. Okay, so we have an exponential formula there that models it for us, and all we have to be able to do is use this formula. So we could be given how many variables do we have there? We've got A, P, R, N, and T, so 5 there is. The idea is we're going to be given 4 of the variables, and we've got to be able to solve for the one that's missing. So in the formula, A represents the total accumulated amount that you have at the end of your investment, or that you're being charged at the end of your loan. So it's the total final accumulated amount. P represents the principal amount, or the starting amount of money, again for a loan or an investment. R is going to be the rate that you're being charged, and it's the one that you're given as a percentage, but we want to plug it into the formula as a decimal. T is the time for the investment or the loan, and that time has to be in years. And then N is the number of times interest is compounded. So it's the number of times interest is compounded. So for instance, if it said the interest was going to be compounded daily, daily would be 365 times for the year. So that means N would be 365. So if N was daily, it'd be 365. If it said monthly, well, there are 12 months in a year, so N would be 12. Or if it said, I don't know, quarterly, quarterly would be 4 times for the year, so N would be 4. Or if it said weekly, weekly would be 52 times for the year, so N would be 52. Annually would be once per year. Semi-annually would be twice per year. Let's see, semi-annually is there, so I don't need to write that one. And I think that just about covers it. Let's go ahead and stick this in here. Semi-annually. That's a weird word to write. Semi-annually would be twice per year. So N is the number of times your interest is compounded for the year. So I'm going to tell you daily 365, monthly 12. Think about how many times per year that is. Okay? So those are some options for values for N. So let's see. On example 3 here, it says, suppose you invest $4,000 at 8.25% interest compounded semi-annually. How much you're going to have total after 5 years? So we have an initial investment of $4,000. That means our principal is $4,000. It's 8.25%, so our rate is 8.25%, which is 0.0825 as a decimal, and that's what we'd plug in. It says it's compounded semi-annually. That means 2 times per year, so n is 2. And it says how much you're going to have total after 5 years. So we know t is 5. And how much are you going to have total, again, means we're looking for that final accumulated amount. So a is our unknown. It's the only variable that's left. So all we have to do is plug in. So we've got 4,000 times, it's 1 plus r over n. So 1 plus r, which is 0.0825 over n, which was 2. And it is raised to the nt power. So up here in the exponent, 2 times 5. And this one doesn't even require any solving. The a that we're looking for is already by itself, so this is literally just going to be plugged into the calculator. So 4,000, 1 plus, come on, plus sign, there we go, 0.0825 divided by 2. And then we'll close that parentheses off and raise it to the in parentheses again, 2 times 5, or obviously if you just wanted to type in 10, that would be fine. And so our final accumulated amount is $5,992.53. Okay, so what's happening here is you invested $4,000 into this account or whatever this is, and after 5 years of 8.25% interest being compounded semi-annually, you end up with $5,992.53. So if you started at 4,000, let's see, let's subtract out that 4,000. That means that you've earned $1,992.53 in interest. So that's $1,992.53 in interest. Almost $2,000 in interest. Like, that's a lot of money, okay? Just for plopping that $4,000 down and letting it sit in this account. Now, not many accounts pay 8.25% interest compounded semi-annually, but if you could find one of those, that's a good way to make money. Okay, let's try another one. Same formula, but we're going to be looking for a different aspect this time where we're going to actually have to use some of our skills from this unit. So it says, suppose you invest $7,000 into a savings account. 30 years later, you have $24,789 in the account. A good growth there. If the interest was compounded semi-annually, what was your interest rate? So in this one, we have a starting amount of $7,000. That was here. You invested $7,000. 30 years later, so t is 30, you have a final amount of $24,789. So we know the final amount is $24,789. If the interest is compounded semi-annually, so if n is 2, what is your interest rate? So this time r. R is the question. It's the one variable that's left, and that's the one they're asking us to find. So let's plug in what we know. Okay, we know a is $24,789. That's going to be equal to p, 7,000, and then 1 plus some rate that we're looking for over n, which was 2, raised to the n times t, so 2 times 30th power. So how do we solve this equation? This is actually not an exponential equation to solve anymore. We started with an exponential function, but our variable isn't an exponent. So we technically should know how to solve this. Let's see. We're going to try to get r by itself. First, let's go ahead and divide over the 7,000. And I don't think that's going to divide nicely. Let's see. If it doesn't, we'll just leave that as a fraction so that we don't have to round several times. And yeah, not going to divide, so we're going to leave it as a fraction. So we're going to have this 24,789 over 7,000 equal to 1 plus r over 2 raised to the 60th power. How do we solve from here? Well, I'm trying to get r by itself. Okay, I can't do that because it's trapped in the parentheses. And in order to get rid of the parentheses, I got to get rid of the 60th power. How do I get rid of the 60th power? Well, it's just like if I was getting rid of a square, I could square root. If I was getting rid of a cube, I could cube root. If I was getting rid of a 4th power, I could 4th root. So if I want to get rid of a 60th power, guess what I'm going to do? I'm going to take a 60th root. First time for everything, right? Let me just move this so I have space to do it. So I'm going to take the 60th root of both sides, and definitely not going to make a nice decimal. So we're going to leave that as the 60th root of 24,789 over 7,000, and it's going to equal 1 plus r over 2. So what's my next step? Next step is subtract 1 from both sides. So subtracting 1 is going to give me the 60th root of 24,789 over 7,000 minus 1. And then it's going to be equal to, I still have r divided by 2. So my last step would be to multiply by 2. Now it's going to be the entire side. So it's 2 times the entire thing, the 60th root of 24,789 over 7,000 minus 1 is equal to r. So that was a mess, but doable. And now we're going to go to the calculator. So 2 times the quantity of, I'm going to go into my functions and get my nth root, so I can make that a 60th root. 24,789 divided by 7,000. After the radical, make sure you're outside of the radical. We want to subtract 1. And there it is. So we're looking at, I'm going to have to round this, r being about 0.042, let's go 6. So this is about 4.26%. That was the rate for this particular investment. Oof, right? That was fun. Okay. Unless your idea of fun is not quite my idea of fun. But in any case, this is an exponential application. We started with that exponential function. All right, let's try another one. Same formula. It says, how many years will it take for an initial investment of $25,000 to grow to $80,000 if it's invested at 4% interest compounded monthly? So this time we're looking for how many years. The time is going to be our question. 25,000 is our initial investment, so P is 25,000. We want it to grow to 80,000, so our final amount is 80,000. And it's invested at 4%. And 4% is going to be 0.04 as a decimal when we plug it in. And interest is compounded monthly, means that n is 12. And so this time the only variable we're missing is t. And again, that's why it says how many years. So we're going to have to solve for t. So we're going to use the same formula, plug in what we know. This time 80,000 is equal to 25,000 times 1 plus r is 0.04 over 2, and it is raised to the n times t power. So 12 times t power. 12t. There it is. Okay? This is actually an exponential equation here that we're trying to solve. So we're trying to find the value for t. So we're going to start still by getting rid of that 25,000. Even if it's an exponential equation, we want to get the exponential part alone. So I'm going to divide that over. If this makes a nice decimal, we can write that in place of that huge fraction. So let's see. Yeah, that's good. 3.2. That's a little easier to write. So let's do that. This is going to be 3.2 equal to, let's see what's going on inside the parentheses there. We can put all that together. 1 plus 0.04 divided by 2 is 1.02. So this is really 1.02 raised to the 12t power. Well, this is in perfect shape here for us to rewrite this in log form. We've got 3 components, and that's what we need to rewrite in log form. So rewriting this, we're looking at the log with a base of 1.02 of 3.2 has to equal our exponent, which is 12t. So remember, the base is the base, and the exponent is the answer. Okay? Except we want to solve for t, and t is still being multiplied by 12. So what I need to do in my last step here is divide both sides by 12, and then t is going to be exactly log base 1.02 of 3.2 divided by 12, which is going to be approximately, let's see. So log base, let's get into a separate line here. Log base 1.02 of 3, what in the, these fat fingers, 3.2, and we want that quantity to be divided by 12. So 4.89-ish. So it's going to be almost 5 years for this investment to grow to $80,000. So let's say 4.8. If you said about 5, that would be fine. So less than 5 years, your 25,000 grows to 80,000 by just letting it sit in this investment. That again is a good investment of money. Okay. All right. Let's look at another formula here. Another exponential formula, again seen often in the financial world, but not always. We see this in science a lot, where you have exponential growth and decay of like bacteria or something, but it's continuous. So if the exponential growth or the exponential decay is continuous, meaning it's not going to be calculated monthly or daily or semi-annually, it's continuously calculated. Okay, the rate at which you are growing or decaying is continuous, continuously increasing or decreasing by some percentage. So when it's continuous, you're going to hear that word or see that word in your scenario. Then you use a different function, and the base of your exponential function, or formula in this case, is e. So e is the base of your continuous growth function. So a is equal to pe raised to the rt power, where a is still the total final amount, p is still the principal or starting amount, and it's principal if it's a financial situation. We would just call it a starting amount if it was not financial. R is still your rate, and again we'll still plug that in as a decimal, and then t again is still going to be time. We just don't have to worry about are we compounding monthly or weekly, because it's continuous, and the base of e factors that in. It takes care of that piece. Okay, so the formula actually looks a little simpler. Let's see if we can use it. So it says an investment of $300 is made into an account that compounds interest continuously. That is telling you to use your continuous formula, your base of e, at a rate of 1.5% for 4 years. And what is the final amount? So our principal investment's 300. We have continuous interest, that's telling me what formula to use. Rate is 1.5%, which is 0.015 as a decimal, and then our time is 4 years. So a is going to equal, oh, this is not 3,000, it's 300. So 300 times e to the rt power. So it's raised to the 0.015 times 4th power, and no solving to do here. A is what we're looking for already by itself. We just need to plug this into the calculator to evaluate. So e, and it's raised to the 0.015 times 4, and we end up with, again, this is money, so $318, and then we'll round to the hundredths place, which would be 55 cents. So, oops. So in this account, with the continuously compounded interest, you've earned $18.55 in interest over 4 years. Not as significant as some of the others that we saw, but you're still earning money, which is always a good thing. All right, now let's look at another one where we're going to use the same formula. It says, suppose that at the start of an experiment in a biology lab, 1,200 bacteria are present in a colony, and the bacteria population grows continuously. So the fact that it says it's growing continuously is telling you to use your A equals PE to the RT power formula. So we sometimes call it PERT. Hopefully that's reasonable as to why. So it says it's growing continuously for 4 hours, bringing the population to 2,200. And it says to determine the growth rate. So think about what we're given here. It says we have 1,200 bacteria to start. So that means the starting amount, we'll call that P, is 1,200. and we end up with, after 4 hours, a population of 2,200. So the time is 4, and the ending population, the final amount, is 2,200. So the only variable left is r, which is why we're asked to calculate r. So we have 2,200 equal to 1,200 times e, not a variable. Remember, e is about 2.72, and it's raised to the rt power. So it's going to be 4r up here, and we have to solve for r. Well, this is actually an exponential equation that we're trying to solve here. So we're going to start by dividing both sides by 1,200. Let's get that exponential piece alone. So that's going to cancel that out. Let's see how this looks. 2,200 divided by 1,200. Yeah, I don't want to round that, so I'm just going to leave 11/6 as my reduced fraction, but I don't want to use the decimal and round it off. So 11/6 is my reduced fraction over here. That's going to equal e to the power of 4r. Now again, this isn't a perfect scenario here, and the perfect situation for us to rewrite this in log form. Now because our base is e, we're going to use natural log when we rewrite. So this would be the natural log base e of 11/6 is equal to 4r. Remember, the base is the base, and the exponent is the answer that we were looking for. So this is our new form. Now natural log is already base e, so I wrote it there so that you know that it doesn't disappear. But this could also just be rewritten as the natural log of 11/6, which technically should be in parentheses to make sure that we're taking the natural log of that quotient, is equal to 4r. And so to solve for r, we have to divide. Let's divide by 4, divide by 4, and then we're going to get our rate at some decimal that Desmos will give us. So natural log of 11/6. What am I doing here? Fat fingers. 11/6, and then we want that to be divided by 4. And we are looking at r at 0.152-ish, so about 15.2%. That's a pretty significant growth for this bacteria. Hopefully it's a good bacteria and not a bad one. Okay. Now it says how many bacteria were there 3 hours after the experiment began. So 3 hours after the experiment began. Well, we can actually write a function for this scenario now. If we wanted to write a function, so here's our formula, right? We actually know r, we just calculated r, and we actually know p, so we can write a function. We can find any final amount, knowing that we started at 1,200, and knowing that our rate is 0.152. So if I plug that rate in and plug that initial value in, this formula now, if I plug any time in, I can find any final amount. And if I plug any final amount in, I can find any time. So we might call this the particular function. This is the particular function for this case, this scenario. Okay, so there it is. Now I can use that. And let me, go back to this question here that says how many bacteria, and let's see, how many bacteria are going to be 3 hours later. So how many bacteria, what's the final amount going to be? Let me change colors. What's the final amount going to be after 3 hours? So t is equal to 3. So I have two options, the same options that we looked at on the very beginning of the notes here. I can plug 3 in for t to calculate a, or I can go ahead and put this function in to Desmos now. And let's call it y if you want. Y equals 1,200, and then e to the this is going to be 0.152x. So here's our function now in Desmos. So now if I want to put in, I use different variables, but you can see t is in the same spot as x, so I'm going to put in x equals 3. And in that intersection, we'll say, well, when t is 3 or x is 3, that y, or a, is going to be 1,893.3. Okay, whereas if you just plugged 3 in for t, you'd get the same thing. So you can just put 3 in for t right there, 1,200 times e raised to the 1.52 times, I'm going to have to put that in parentheses, times 3 power. We're going to get, what am I missing here? Oh, I got an extra multiply dot. There we go. Oh, I put my decimal in the wrong spot. I'm like, what the heck? Okay, sorry, there it is. The same answer that the graph is giving us, 1,893.3. Gosh, guys. Okay, I'm losing it. It's the end of a long notes here. Alright, so from the graph, or from plugging it into the function, so from the graph, we can see that a is going to be, a is approximately 1,893.3, but this is bacteria. I don't think we can have a partial bacteria, so let's just say about 1,893. Okay, and now we can finish this off if I can get rid of my calculator. All right, so here we go. Last one. It says, when is the population going to reach 3,000? So this time we're looking for t. This time we're looking for t, and we know the final population is going to be 3,000. So again, I have two ways I could do that. I could plug 3,000 in for a into my particular function and then solve for t, or I can just use the graph since it's already here. Get rid of these guys. Now if I want to put in y equals 3,000, then it crosses my graph there. I can see that when a is 3,000, t is going to have to be 6.082. So from your graph, you can see that it's that t is about 6.0, now I lost it, 28, I said 82. So a little over 6, I think these are hours, yeah. So about 6 hours. It takes about 6 hours for this population of bacteria to reach 3,000. Okay? And again, you could plug those values in and solve by hand, but if you have the function and it's already graphable and you can calculate that way, you can really use either option. Okay? So hopefully I didn't overwhelm you with too much information. Hopefully you've got enough to work on your practice, and fortunately we're nearing the end of all of this, so hopefully you're keeping all of that stashed in your brain and not discarding stuff to make room for new stuff. Whatever the case may be, if you need some extra help, just reach out. I'm here for you. Alright guys, take care.